So yeah, I mean, we're biotechnology solution enabling the renewable water paradigm. And the whole concept is really based on the water cycle. The way we view it, the water cycle is, you make drinking water, you distribute it and use it, you send it to the wastewater plants, and then it goes back into rivers, lakes, dams, reservoirs. If you look historically, you can almost draw a line between the two. This whole area here is all engineered infrastructure and primarily about water quantity. It's storage, it's pumps and motors and pipelines and so on. Up here, we see ourselves as a layer of technology that sits over the top of current infrastructure. And we have our own kind of toolkit, which is very different to the engineer's toolkit. And our focus is on water quality, maintaining water quality throughout the water cycle. That is a biological process, and it's all about nutrient management. So, wastewater treatment is not done by concrete and steel and pipes and motors and pumps. What you're trying to do is create an environment in which the biology can take place. So what we look to do is turbocharge and boost the biotechnology, or the biological processes. We have offices and manufacturing facilities in Australia and the US, and we have successful projects in every continent in the world, basically. So I want to start off by talking about eutrophication, and I'm going to jump around a bit just because I want to make something very brief and simple. The conventional view of eutrophication, people look at all the symptoms and then go and try and attack the symptoms one by one. So we put phosphorus precipitants in, the phosphorus goes to the bottom, it gets remobilized, and you're back to square one. You put weed killers in, you put algicides and things like that. That biomass dies to the bottom, decomposes, the nutrients are remobilized. So you're really just playing whack-a-mole. Our approach is very much firstly based on systems theory rather than Newtonian science. And we're sort of saying, if you keep doing what you're doing, we all know what happens, this frog in a pot sort of syndrome. So if you look at it from a biological point of view and a systems theory point of view, then the analysis is very different, because you basically say, there's two types of ecosystem, aerobic and anaerobic. You have a primarily anaerobic environment where the problem is. And that leads to nutrient recycling. And the fact that the nutrients are recycled over and over again means your food web is impaired. And it is through the food web that you get nutrient clearance. So your nutrient clearance is blocked. We can then re-articulate that in systems theory terms. And we say here the system attractor has changed. And this is kind of systems vernacular, I guess, but it's all relevant. You have action at the margin really being the bottom of the lake, reservoir, dam, or whatever, at the water sediment interface. You had feedback, which one of the major ways that manifests is in nutrient recycling, until you reach tipping points where you get dominance of weeds, algae, and cyanobacteria, and that's in systems theory called the system regime change. And once you get to that point, you've lost your requisite variety, which we call biodiversity, and then you've lost the inertia of the system to disruption, and it flips into a eutrophic state. I just want to quickly address cyanobacteria. There are various factors in a eutrophic water body that favor cyanobacteria, and that's kind of the inevitable endpoint that you get to. And the anaerobic benthic condition creates ammonia, which your microcystis can use as a nutrient. Virtually no algae can use it as a nutrient. A stratified water column, the cyanobacteria can navigate up and down. They can dive down to where the nutrients are and then come back up to the top where the sunlight is, and the other algae and so on can't do that. So they start to take over and dominate. And increasingly what people are starting to realize is this phenomenon of cyanobacterial succession. And what that is early in the year, kind of round about now, the gliotrichia, they sit in the bottom, almost hibernate, and they start to germinate and they mobilize nutrients. Typically then they are succeeded by anabina and phanazaminon type cyanobacteria as the water warms up and so on, and then later the microcystis take over. So they're all different cyanobacteria, but it's almost as though you've got team cyanobacteria, exploiting and manipulating the environment in their favor. Now, if we go to this term eutrophication, a lot of people think it means too much nutrient. It actually means well nourished. So that immediately says, well, then let's look at the nutrient cycle to understand what is going on with the nourishment from the nutrients. And the nutrient cycle, in its simplest terms, it's just nutrients become biomass, biomass become nutrients. In an aquatic environment, your primary production is via photosynthesis. So your algae, weeds, and cyanobacteria dominate the nutrient uptake. They die off, they fall to the bottom and decompose, and that's your sort of primary nutrient cycle. In order to keep balance, you need the heterotrophs, which is the zooplankton, the crustaceans, the insects, the fish, and so on, to consume that primary biomass. And you need full biodiversity so that you have a full food web. At the apex of that food web, you have fish, which are, fishermen take them out, birds of prey take them out, animals such as otters and bears and so on will take them out. So you have a means of nutrient clearance out of the water body. And in essence, what happens is your food web gets starved off and your weeds, algae, and cyanobacteria totally dominate the nutrients, and they just recycle perpetually. So conceptually, in order to rectify that, you have to reverse that. And that's kind of logic, not science almost. So how we do that, in essence, there's three legs to what we do in a eutrophic environment. Firstly is create an aerobic aquatic environment, and that's throughout the water column and also the upper levels of the sediment. Then we have to break that nutrient recycling loop by restoring the food web. And then we're able to get nutrient clearance and balance. So we have sort of proprietary technology and so on and ways that we do that. Enzymatic digestion, I just want to make this point because a lot of people are still trying to put bacteria into lakes to remediate them. Bacteria are used in wastewater treatment. The idea being the bacteria will take up the nutrients to produce a bacterial sludge, which in a wastewater environment, you can separate that sludge from the water and then you remove the nutrients from the water. There's absolutely no logic to pumping bacteria into a lake, river, dam, or reservoir in order to create a bacterial sludge, which settles to the bottom and increases the nutrient stockpile at the bottom that all your invasive species and algae and cyanobacteria are going to exploit. So rather than bacteria, what we do is use enzymes. And this is just to prove the point. We had one of the state DEPs wanted to understand this. We use this as an analogy, saying that Alexander Fleming, when he discovered penicillin, is basically an enzyme. What they also figured out soon after that was if you put small amounts of additional synergistic biochemicals with it, you could ramp up the performance of the enzymes incredibly. So that's the kind of, one of the biotechnological ways that we've gone about it. And the important thing to understand is that when Alexander Fleming figured out that penicillin could do what it does, he didn't say gobble up lots of bacteria. There's a far more effective way of going about things. So now switching to the wastewater type environment, this is a typical situation that you get in a lot of wastewater plants where the sludge is just not digested. The digesters become basically inert. So this is undigested sludge taken from a completely dysfunctional anaerobic digester, put into a tub with a sealable lid so that we can maintain anaerobic conditions. And I think twice a day for 2-3 minutes, we just took the top off and stirred it. This was within 2 days, that was within 5 days. So we digested that organic sludge and created liquid out of it. What we then did was oxygenate it, and I think within 7 days, we got to that sort of situation. So at a very basic level, that illustrates it. This is a bit more sophisticated. This is data taken from a situation. You'll see in 7 days, treatment of an anaerobic digester. This is the sludge coming out of it. And you can see how beforehand it was basically undigested, and afterwards we've got a good result. This is then an activated sludge plant in a wastewater treatment works. This is how dysfunctional it was. That is the treated wastewater in a clarifier. This is the same clarifier, I think about 8 to 10 weeks after we'd commissioned the whole solution. And the camera will just go up so you can see it is in fact the same place, because some people give you before and afters which are actually one place or another place. Here's the data for that. You'll see on the right hand side the standards that was to be achieved, on the left hand side what they were actually achieving. That so-called treated wastewater is probably higher in contaminants than most raw sewage coming into wastewater plants. This is what we got it to, which was compliant on every one of those parameters. This then is lagoons. What we did at this plant, they had abandoned the use of these maturation ponds because they just sludged up and filled up with sludge. We recommissioned them and took the wastewater from the clarifier, the water parameters that I've just shown you, and put it in here for further treatment. And this was then the water being discharged from the oxidation ponds. And what we did to prove a point was test that against the standards for potable water. Now, we don't claim we produce potable water, we don't get into that. But on a lot of the major parameters, we were compliant, and that proved the case that we're able to create renewable water, so that, from a wastewater plant, we can produce water of a standard that could go straight into a purification plant without going through the whole solution to pollution is dilution, and that dilution becomes eutrophication. So then this is just jumping around. This is a lake where, if you look up at the top here, that's a 2-foot contour. So the whole of the top end of this lake was completely filled with organic sludge. The average depth of the lake, just over 4 feet. The volume of the water, 150 acre feet. 2 years later, the average depth is nearly 7 feet. The volumes increased by 215 acre feet, by 65 acre feet, which is 100,000 cubic yards of sludge and sediment that we've digested. And you can see that in the change in the contours. What we can also do is draw a transect and look at that lake in profile. This is before, and then do the same afterwards. And you can see the difference, and you can see how we have digested that sediment and changed the profile of the lake. That's a 5-foot contour before and after. Another way of illustrating the point. This is a heat map of the weeds, again, before and after, and you can see the extent to which the weeds have thinned out. This is another one, aerial view before and after. So when we turned our radar system on, it was completely topped out with weeds, and a year later, we have that. This is another one, a before and after. This is an interesting one, Bowling Green in Ohio. It's on the Maumee River. The Maumee River, which is to the right here, in summer is just pure cyanobacteria. And they have a relatively small reservoir. They can only hold, I think, just under 30 days water supply. So they have to keep drawing all the way through winter, through summer. So this is the sort of situation they were encountering, where the water drawn from the river had 150,000 cells per mil, and in the reservoir was hardly any different, even though they were nuking it with peroxide. But the real problem was cyanobacteria. So we commissioned in April 2017. If we look at the equivalent time, so it's kind of end of July, first week of August, the phycological count in the river is pretty much the same, slightly worse. You can see the difference in the reservoir, and more significantly, you can see the HAB level in the river, and we have it under control in the reservoir. Similarly, this is a reservoir in Puerto Rico where they could not produce potable water, because if they drew water from the upper levels, it was so full of algae, cyanobacteria, and so on, it clogged their filters, and they couldn't get on with it, couldn't produce water. If they drew it from further down, it was bad taste, geosmin, hydrogen sulfide, and so on. We fixed that up pretty rapidly. The interesting thing, sorry, it's on automated there. The interesting thing was that the fish populations were restored, the pelicans came back, the fish eagles came back. That proves this whole thing of the food chain will clear the nutrients if you're able to manage it that way. This was the amount of chemical used the year before we commissioned. They ran it for a year, 2013, and in 2014, they halved their chemical requirement. What that did was that they'd had a problem previously complying with TTHMs. So on Cyanobacteria Reservoir, they have 2 water purification plants, Site 2 and Site 3, which are both compliant now under the 80 microgram per liter, whereas this, which is on a nearby reservoir, is still not compliant. So, kind of the gift that keeps on giving. This is a lake in New York, and you can see there in 2017, I mean, it was just shut to the public virtually all the way through summer. 2018, we commissioned it, and since then, they virtually haven't had a problem. So that's HABS as shut down by the health department. And then this is another one, drinking water reservoir in, it's up near Pittsburgh, and same sort of thing. You've got a whole lot of different parameters. They don't have a cyanobacteria problem at all, but we're able to improve their water quality in a number of ways. That's a before and after, and this is just an interesting one. This was here in South Africa. Beforehand, they had a cell count of nearly 4.8 million. It was 100% cyanobacteria. And within about 4 months, we got the cell count down, but you can see the biodiversity coming back at that phycological level. So, in terms of being a leapfrog technology, which was kind of the way I see it, that's what it is. We're able to take situations that are completely overwhelmed. Just to give you some local relevance, in South Africa, you have a situation where up here, Johannesburg and Pretoria is the economic hub from the days of the mining boom. You have the Lesotho Mountains there. Rain basically comes in off the Indian Ocean, dumps on the mountains, and historically it always flowed back into the sea. Around about 20 years ago, I think it was, they started to change that. This is the Vaal River system, Vaal Orange River that runs to the Atlantic, and you have the Limpopo that runs to the Indian Ocean. So about 20 years ago, they built a whole lot of dams and tunnels and re-engineered it so they could redirect that water into the Vaal River system. From there, they pump it up to Johannesburg and Pretoria, the industrial commercial center. And from there, most of it goes through wastewater plants and discharges into Hartbeespoort Dam. So this is where it is in this sort of context. You can see Johannesburg and Pretoria. The wastewater treatment plants all going there, and that's what it looks like. It's supposedly one of the most eutrophic dams in the world. Our whole proposition is they're currently spending, I think it's about $3 billion in Lesotho Highlands Phase 2, where they're going to pump even more water from Lesotho into Hartbeespoort Dam and just compound the problem. So at the moment, they have 700 megaliters a day of treated wastewater going into that dam. Once their solution comes on stream, they're going to have 1.2 million, 1,200 megaliters per day going in. So the solution is going to make it worse. They have a similar problem just north of Pretoria. This is a big wastewater treatment works. It goes down to a dam, and at that dam, they've just spent an unholy amount of money on the water purification plant. And because you've got engineers operating in silos, what they didn't take account of is this wastewater treatment plant is a complete mess. The average retention time in this dam is about 10 days. They were pulling out the equivalent to about 1/10 of the water from that reservoir per day. They spent $50 million upgrading the plant so it could draw twice as much. That's halved the retention time in the lake, in the reservoir, and the water quality, they've got all these things here after they hailed the plant, they're saying 2 years later there's been no improvement. Well, we could have kind of told them that. And they're about to make the same mistake. And this is why I've got meetings scheduled with the Ministry of Water Affairs. This is yet another dam. This is yet another wastewater treatment plant. They've just, towards the end of last year, had a whole big publicity thing. You have the same situation going on. That is the dam, and they've got a big mega development that they are doing here, and they're going to have the exact same problem. They already have a cyanobacteria problem in this dam, and what we're saying basically is, that's what we do. So that's the renewable water paradigm. In Bangladesh, they have problems with their sewer lines clogging up that they have to clear manually. So again, we can address that. And the project we're looking at there, this is their lakes and rivers where the water is so black, not even algae grows in it. The only thing that can grow is floating aquatic vegetation where, it can grab the sunlight above the water. So that's the sort of area that we're getting pulled into. And that's the end of the presentation.